Here again and welcome to Chemcracker. Today we're looking at weak acids. Now last time we looked at strong acids and we said that they're fully dissociated in aqueous solution. Well, for weak acid it's almost the opposite. In fact, they are only slightly dissociated in aqueous solutions. You go to a lot of books, they say it's partially, but that is not really a very good description of a weak acid. A more accurate description is that weak acids are only slightly ionized, only slightly dissociated in aqueous solution. Now, if we consider a weak acid HA, what we find is that when it dissociates in aqueous solution, only a few ions, relatively few ions are formed compared to the number of molecules. So what it means is that this equilibrium lies to the left. The position of equilibrium lies to the left. For weak acids, we can write an expression for the equilibrium constant, which is called the acid dissociation constant, Ka. And it is given by, of course, the concentration of the products, which are the ions, raised to their stoichiometric coefficients, which are 1 and 1, over the concentration of the acid, HA. Now we can make a couple of assumptions. First assumption we can make is that the H plus concentration will be equal to A minus concentration. And we can make that assumption because it's a 1-to-1 ratio here for the dissociation. But the real reason why I can make that assumption is that the H plus ions produced from water is negligible because water is only slightly ionized. So we can make this assumption. The other assumption that we can make is that the concentration of the acid remains constant. And we can make that assumption because it is a weak acid. Only a small proportion will break down to give you ions, which means that the concentration of HA remains relatively constant. Now, if we make those two assumptions, we can rewrite this expression to be H plus concentration squared, if we substitute H plus for A minus in this here equation here, over HA. Now, what that does, it allows us to do two things. It allows us to calculate the value of Ka if the H plus concentration and HA concentrations are known, and it also allows us to calculate the hydrogen ion concentration, hence pH, if we know Ka and HA concentration. And we're going to look at calculating Ka. Let's look at an example of calculating the acid dissociation constant. Now this example says that I am to determine the Ka of methanoic acid if a 0.01 molar methanoic acid solution contains 1.33 times 10 to the minus 3 molar H plus ion concentration. Now we can write the equation for dissociation of methanoic acid as HCOOH dissociating to give H plus and HCOO minus concentration. Now, therefore, we can write Ka, expression of Ka to be H plus concentration times the methanoate ion concentration over the concentration of the acid. Now, if we make the assumption that H plus ion concentration is equal to the methanoic ion concentration and that the methanoic acid concentration is constant, we can rewrite that to mean H plus concentration squared over HCOOH. Now, since we have both a hydrogen ion concentration and we have the concentration of the methanoic acid, we can fit that into the equation here and write Ka equal 1.33 times 10 to the minus 3 squared over 0.01. And if I work that out, answer will be 1.77 times 10 to the minus 4 mole per dm cube. And that's calculating Ka of a weak acid. Don't forget to drop us a like here on Chemcracker, share the video, make a comment, and subscribe for more Chemcrackers.